Welcome to the first part of the Australian National Curriculum for Year 9, and this is a review of basic algebra from Year 8. So let's see how much you remember. And anyway, what is algebra? Here's my burning hot first question here. What is algebra anyway? So you can Google search that and you'll find that it comes from the Arabic, Arabia, algebra, meaning reunion of broken parts. Do you remember anything that you did in algebra that suggests that you're uniting broken parts? Let's go back and have a look at that so that you can play catch up if you weren't sure of algebra the first time round. And here's the guy over here, Al-Khwarizmi, I think that's how you say it, the father of algebra, or purported to be. Okay, he lived in Baghdad around 780 to 850. He was one of the first, after birth of Christ, AD. He was one of the first to write about algebra using words, not letters. Okay, and I guess there's your first clue. Do you remember that algebra involves using letters in place of missing numbers or maybe broken parts? Not sure. Around 825, he wrote the book. Here we are. I'm not going to try and pronounce that. From which we get the word algebra, restoration of broken parts. This book included many word problems, especially dealing with inheritance. Well, it's gone on from there, of course, and we use it in completely sort of different ways now, I guess. And let's have a look at how we can put our broken parts together, if you like. So come on down to the first little thing that you might look at, and that's this. We in maths generally work with numbers, 5 squared plus 3 squared, whatever that is. I'm going to ask you to work that out later on. So what could a squared plus b squared mean? And there's the first little inkling about how we do use algebra to solve problems and to look at patterns, particularly in maths. What could a squared plus b squared be? Well, a could be standing for a number, and so could b, as you know from before. So in this problem, a could be 5 and b could be 3. But we don't know, so it may not be those two specific values. It could be other values. And there's the first idea of one of our tools of algebra. We introduce letters standing for numbers. And I don't know whether you remember the word for that. It's a pronumeral where a letter stands for a number or replaces a missing number. Okay, so time to try to remember some of these things. And you might note that down in your notebook of that particular word if you haven't remembered it. Okay, so come on down now and let's have a look at how we use it and start this idea of reunion of broken parts, I guess. Here's a word problem. I don't know whether the father of algebra had one like this. I think his might be a bit more complicated than this. But we want to put all these parts together and find what the number is, if you like. You could think of that in that way. I think of a number, double it, add 12, and the answer is 25. What is the number? So you can sort of use words and work backwards, but in algebra land, we've gone to symbols now, or letters to take the place of the number. So do you remember how to set this problem out? Let's have a look. Let the number be, well, you usually use x, don't you? But let it be n for number. Let's be very flexible here. So double it, that would be 2 times n. Add 12, here I'm going along here. Add 12, and the answer is 25. So the answer is, we put in an equal sign. Hey, can you see what's happening in algebra land here? We're introducing some symbols and conventions and setting out that is special to mathematics. It's like the jargon or the language of mathematics. Can you notice here? I have not put 2 times. Doubling a number is 2 times, and we leave out the timesy, don't we? Do you remember that? Okay, so there's our problem in, if you like, a mathematical sentence or an equation. A mathematical sentence in maths, in algebra land. Or we call it an equation because it's got an equal sign in the middle of it. Okay. I'm just going to creep up slowly on some of this old stuff so that you can recall the language and the methods here, and then we're going to practice some of it. All right, so how would you solve the problem? What is the number? Well, what we could say is let's have a look at the number. There it was there. Well, that stood for the number. And what's been done to n? It's been times by 2 or doubled. Then 12's been added. And the answer is 25. Shall we unpack it? Let's go opposite operations in reverse order. Let's subtract 12 from both sides. That would leave 2n on this side. 25 take 12 would be 13. And then we could reverse the doubling. Let's divide both sides by 2. So n is 13 over 2, or n is 6.5 or 6.5. Okay, so you do need a process with this one, because that 6.5 was not very guessable, was it? The whole number ones you can guess. But some of these other numbers, where you have fractions, then you need a system. Now, I want to add something to this. I don't know whether you've seen this before, but when we go from one line in an equation to a simplified or the next stage, we put an implied sign. So that leads the story on. From here, this implies this, and then that implies this. We can leave this out now. I hope you got to that point last year or in year 8. And therefore, these are our punctuations or leading on points in our mathematical journey, or our story, or our solution. Please note, as you're in year 9 now, you're moving up in mathematics land, we try to look at a solution in maths, not just the answer. We want to know, hey, how did you get that? So you should take quite a lot of pride in the way you set out a solution. And this sort of thing over here with the implied signs can be a nice bit of sophistication to bring to your story, rather than just a whole lot of scribble. So in this year, in this Year 9 National Curriculum subject now, we want to bring up the level of sophistication. Sorry, get rid of that. Okay, let's come down now, and I've gone too far, so we'll just go here to this one. Let's go to more putting the union of parts together and looking at patterns where you have different problems with different parts if you like, but some things are in common. The radius of a circle is 5 centimetres. What is its area? Okay, is there a pattern in all those problems? Yeah, well, I guess you've been taught the area is pi times the radius squared of any circle. So putting all those circles together, we can find this, if you like, is a summary of the pattern that occurs in all of them. A equals pi r squared. And so we can say, well, in this case, r is 5. So in our case, that leads to, or implies, a is pi times 5 squared. And so on. And you can work that out on the calculator. And it would be in centimetres squared. So we want to put that there. And then you have a question of what level of accuracy would you like there? Because pi is an irrational number. The decimal keeps going. Pi is approximately 3.142 to 3 decimal places, but it keeps going. So if you multiply that by 25, you will have to round it off. And usually we round it off to 3 significant figures. But here you use on your calculator pi, all the decimal places, times it by 25, and then state your answer to some level of accuracy, depending on the problem and the situation. 3 significant figures is quite common. I'm not going to go into that there, we're getting a bit sidetracked here. But what I'm trying to pick out here is the uses of algebra. So there's 2 main uses of algebra here. To describe patterns and to use them, and to substitute into the pattern formula if you like, but also to use pronumerals to solve problems. Okay? Putting all the parts together if you like. All right, are you ready to try and put some of this together? I hope you're remembering some of these things that you've done before. Okay, come down now, and here's my question. Does 5 plus 3 squared equal 5 squared plus 3 squared? And why have I stuck this here? There's no letters, it doesn't seem to be algebra, but it does involve some aspects of algebra, because what we're doing is looking at, if you like, symbols and notation that we use to mean certain things in maths. So the first thing you see here is, what do these squares mean? Okay, so we've got to revise some of that mathematical language, that notation. So a square, let's use a letter now. A squared means A times A. So 5 plus 3, or a bracket. I think you've also learnt some systems in maths where it says bed maths, brackets are done first to isolate that term. So what does this mean? Let's have a look. 5 plus 3 times itself, where A here has been replaced by the big bracket 5 plus 3. Do you get it? Okay, so pause the presentation. Are those two equal? It seems reasonable, sort of, to say that they would be, but are they? Pause it and see if you can work it out. Okay, coming back, let's have a look at 5 plus 3 squared. So that's really, you've got to do the brackets first. 8 by 8, which is 64. Okay, so that's the left-hand side. Let's work out the right-hand side. 5 squared plus 3 squared is 25 plus 9 is 34. They're not equal. So the answer is no, they are not equal. And this is something we're going to investigate later on. Well, I won't put a question mark, they are not equal, but can you understand it? That's what the question mark was for. Can you see why they may not be equal? We're going to answer that question later on in some exercises. So, interesting, isn't it? We've got some symbols, symbols, I've left out the B there, symbols and notation to remember as well. The language in mathematics, to make it easier to write out without lots of words. Okay, come down now and let's have a look at some examples. Now, these are laws and symbols and methods and language that you are expected to know from year 8. So you might have to go back and revise some of this. This is, these screen clippings are taken from the Hayes and Harris Year 9 Australian National Curriculum textbook. So you can see it there, and you should have that book handy by. So this is A and B of that chapter, chapter 5 I think it is there. And let's have a look at this first law. It's called the distributive law. You don't have to know the name, but it helps to remember what's going on, because we're distributing, see this, 2 times 5 plus 3 means 2 times 5 plus 2 times 3. So you're distributing the operation of multiplication over the operation of addition. So it's a little notation that means you've got 2 lots of 5 plus 3. So you'll have 2 lots of 5 plus 2 lots of 3. That's our little bit of language there, if you like, or notation. So that's our first law or notation to describe what we're going to do with this problem. So here we are, here it is in words. To remove a set of brackets from an expression, we multiply each term inside the brackets by the term in front of them. We then add the results. Okay, so notice we would work that out. 2 times 5 is 10. In pronumeral land, so we're describing this situation for any numbers, not just 2 and 5 and 2 and 3, we will use symbols and we don't have the multiplication sign. That's not in between them. We leave that out. Do you remember that from your earlier work in algebra? Okay, so there's the rule. But you know, with Honey Maths, I want you to always say why. So why is that so? Let's try and understand it, not just have a rule. What's the idea? Well, the idea here, of course, is that back up here, I've said it before, this is a symbol for 2 lots, 2 times of 5 plus 3. So you're going to have 2 5s and 2 3s in there. I mean, you could look at it in many ways. You can draw a little picture of that. But that's the idea. So it's only a notational thing here. Don't go memorising lots of rules without thinking about the concept and so on. I've got to stop that. Okay, come down and let's practice some of this. Here's some examples from Hayes and Harris. I'm going to go through these slowly. If you get bored, go forward in the presentation to a point where you are not so sure and you have to do some revision and practice. Okay, let's just expand the following. Now there's the word expand. So it means make bigger, make larger, doesn't it? So we want to know that this is being compressed, if you like. What's it really stand for? Well, here we are. It stands for 3 times 4x plus 3 times 1. And generally you might leave that line out and just do it in your head. So 3 lots of 4x, let's keep that simple. Here's 4x's here, and another bundle of 4x's here, another bundle here. How many you got all together? Let's add them up. 4 plus 4 plus 4 is 12x, or 3 fours are 12. Remember, multiplication can be, in simple situations, thought as multiple addition. Right? Instead of adding 4 plus 4 plus 4, you can multiply 3 by 4. Okay, get the idea. What about this one here? What does it mean? It's standing for 2x lots of 5. You don't happen to know what x is, that doesn't matter. X is a number. It'd be a bit more friendly in your thinking, I guess, if you did know what the number was. And then it's 2x times negative 2x there. So that's 10x. And what's this one? 2x times negative 2x. Okay, we've got two problems here. It's a positive times a negative. Just remember what that means. If you've got neg 2x, so let's make that neg x, so we're down at neg 2x on the number line, and then we have more lots of that staying in the same direction, so you're going to be moving further down here. You're going to go down to negative, positive times a negative, because you're still moving in this direction on the number line, is neg 4 and x times x. Oh, there's that notation again. We're multiplying a number by itself. That's a symbol of a square. It's starting to build up, isn't it? The knowledge that you're supposed to carry. And that's the idea of maths, of course. As we build up, maths learning is sequential. Here's a Huddyism. Is sequential and cumulative. And that's why many people have trouble with it. They forget stuff from before. And we want to keep accumulating. Accumulating is the verb, but the adjective is cumulative, no accumulative. So here we try to accumulate and build up all our knowledge and build into the area of mathematics as a whole subject. So you can't forget stuff. That's why you might find maths a bit harder than some other subjects at times. Okay, what about this one here now? So it's neg 2x times the first one and neg 2x times neg 3. So here, neg 2x times x plus neg 2x times neg 3. You can leave this line out if you're good enough. Neg 2 and x by x is x squared. There's that notation again. But neg 2x by neg 3 is plus 6x. You have here a negative direction times a negative. What's that going to do? Do you remember? Here, you might have neg 3, and then you want neg 2x lots of it. Okay, so the negative there is going to reverse your direction. So it's going to be on the positive side up at 6x. Okay, so that idea, and that's our fundamental thing going right back to directed number work, where a negative means change in direction or the opposite direction. So hence the rule negative times negative is positive. You should always try to unpack that rule and go up the Huddy's hierarchy of maths learning, which is not just the rule. Remember this now. It's not just the rule. So there's the rule or the algorithm. You've then got the concept or what's really going on, and then try to get to the level of, I see it. I actually get that. I see what's going on there. So try not to stay down here just learning rules. Try to say, hey, what's the idea there? And really push up that hierarchy to get up close and familiar with maths. And maths is fun if you get up close and familiar with it. Okay, come on down now to another example here. And as I've been saying in these, you've got to watch this negatives in there. So let's have a look at this problem. 2 times 3x take 1 plus 3 times 5 take x. Let's do it. Here it is. The distributive law to both of them. Writing it right out. You can leave this out and just go to this line if you want to. And then 3 times 5 take 3 times x. The distributive rule again. The number in front has to be, or the term in front, there's another word, term, if it's got letters in it, term in front has to be multiplied by everything in the brackets. So then we work all the steps out here. And now there's something which we call collecting like terms, isn't it? Do you remember that from before? Collecting like terms. So there's a 6x, there's a take 3x, so you'll have 3x. Can you do that? Well, x stands for some number, we don't know what it is, but x will only have that one value in that problem. We're letting x in this problem stand for some particular number. Although we don't know what it is, that x in the problem and that x in the problem mean the same thing. Okay, so neg 2 plus 15 is plus 13, positive 13. Then we have one with x's in it. So it's the first term by each of these, and then take 2x by each of these. Now, what this little dude over here is talking about is this negative sign in here. Just let's watch it now. It's x by 2x plus x by neg 1 in the first bracket, then neg 2x by 5, and neg 2x by neg x. So this is an important idea here, that 2x has a negative sign. Negative sign. Look at that abbreviation there. Negative sign. To its left. The sign of a term, we read from left to right, the sign of a term is in front of it. So that 2x is actually neg 2x, that little sign in there, neg 2x. Okay, so let's multiply them all out. X by 2x is 2x squared. X by neg 1 is neg x. Neg 2x by 5 is neg 10x. Neg 2x by neg x is negative times negative is positive. 2x by x is x squared. Okay, so we then can collect up the terms that are like each other. The squares would be the same number. So this is 4x squared. Then take x, take 10x. Oh, we've got to look at that. Take x, there's one little x down negative on the number line. And then another neg 10x. We'd be down at neg 11x. Just remember that work with directed numbers. Okay, so are you getting the hang of it? I'm doing it all now. This is all supposed to be revision. You might have to pause this and go back to the textbook in section A and B and do some practice problems, because what I'm going to do in a minute is give you a little review exercise to see how you've done. So if you're getting lost along the way, you need to go to the textbook and do some of these. All right, let's go back now to the last thing here. Not go back, go forward. The product, what are they doing here? What did that mean? Okay, so let's not get mesmerized by the symbol stuff. Let's see if we can understand what it means. We're timesing two things together. We've got A plus B as a number, lots of C plus D. So what we're saying down here is overall we would have A lots of this bundle plus B lots of this bundle. And so we've added up the two bundles of C plus D. We've got, let's say, 3 lots of C plus D and 4 lots of C plus D. We would have 7 lots of C plus D, 3 plus 4. So that's all the A plus B is saying. If you have bundles which are common, C plus D, and you've got 2 of them, you can add them up. So that's again, understanding the notation. So here, we're going to do the same thing again. AC plus AD, then BC plus BD. So the only thing new here is the idea of 2 brackets times. And then we can unpack that by breaking down the first bracket and multiplying through the second one using 2 distributive rules, if you like. This is the same as what we did before. The only thing that's new is the way it looks when you have a bracket with 2 terms in it times another one. Can you see the notation building up here now? Let's have a look at those problems and then we'll finish this little bit here. Okay, so here we are, expand and simplify when you've got 2 brackets. So again, it's only a system of representation that you need to think of here. So you will have x times this bracket, so it'll be x times x, x times 2. And then the 3 times the other bracket. 3 times x plus 3 times 2. And what the little dude's saying over here, you could do that in your head and get to here as you go. X by x is x squared. X by 2 is go straight down there, if you wish. This is sometimes abbreviated to FOIL. FOIL. Firsts, outers, inners, lasts. I might have seen that before. What it says is every term in this first bracket has to be times by every one in the second bracket, and similarly, so here 3 has to be times by each of them. So it's just a system to say don't leave any out. So let's write it down. It's the firsts together, the outers, that's just what we did, the inners, and the lasts. Okay, all right, so that's just a system for doing that. Let's now go and simplify our answer. And so we've got only 1x squared, so that stays there. We've got two terms that are like each other here. 2x plus 3x is 5x. Then we've got plus 6. So group those up and simplify it. Okay, what about this bracket here now? Same thing. Start with the first bracket. 2x times 3x, 6x squared. 3 times 2 is 6. X by x is x squared. Are you good enough? 2x by neg 2 is neg 4x. 1 by 3x is 3x. 1 by neg 2 is neg 2. So there's only one x squared term, so it stays a 6x squared. Then neg 4x plus 3x, they are like each other. Let's go along the number line here. Neg 4x down there, and then plus 2x, or plus 3x, sorry, would be back up here, which is just neg 1x, or just neg x, and then the neg 2. Do you get the idea? Try and keep in your mind, you don't have to draw this diagram, but keep in mind how to work with directed numbers. Okay, let's keep going. You'll get a chance to practice in a minute. And this is the last little set, and this leads on, these two are special cases, and leads on to the next presentation. Expand and simplify this one, and this one, this one, and this one. And can you see how these two types are special examples of this? What's special about them? Okay, they are two brackets times. I want you to pause the presentation, perhaps discuss it with classmates, with the whole class. Why are these two cases special examples of the general form of two brackets times? Okay, pause it, and we'll come back. Okay, back again. Can you see it? Did you see it? Well, these two brackets are special, aren't they? How would you describe that? I know, let's do it in words. You have a first term, plus a second term in the first bracket, that's x plus 3, and then you're multiplying it by the same first term minus the second term. So that is special, because these match up with the terms in the first bracket. Can you see that? X plus 3, x take 3, so there is something special. And this one, 3x take 5, 3x plus 5. So you can put the brackets in either order, but they follow this sort of pattern. Would you like to try to write that in a general form using general symbols as we do with distributive laws and stuff? What would you write? Pause it and see if you can work it out. Come back now. You'd say this is something like a plus b by a take b, wouldn't you? Isn't that the pattern you're seeing here? Hopefully you saw some of this in year 8. We'll see how you go. All right, what about this one then? Just looking at the patterns now, we'll work them out in a minute. What'd you get for that one? Hey, I think you can see it's a square. So the two brackets are actually the same. It's the first term plus or minus the second term, because that's a minus in that one. And you multiply it by itself. So you're actually going to do this. First term plus second term by first term minus second term. Oops, sorry, plus. Oh, gone back to the first one. So it's what's called a perfect square. It's just the same bracket times. So both of them are special cases of this. Let's do them now. So come back up to example 4. We'll put the two brackets together like that. And now it's x by x is x squared. X by neg3 is neg 3x. 3 by x is 3x. 3 by neg 3 is neg 9. Uh-oh, look at what happened here. Because of that positive and negative signs being different in each of the brackets, that disappeared. Neg 3x plus 3x comes to nothing. So you have no x term left here. It's simply x squared, there it is, take 9. What happens over here? Let's see if it works again. 3x times 3x, 9x squared. 3x times 5, 15x. Neg 5, don't forget the negative, times 3x, neg 15x. Neg 5 times plus 5, neg 25. Oh, it's done it to us again. Plus 15x, take 15x, 0. If you've got 15 times the mystery number and you take away 15 times that mystery number, you have nothing left because x is the same number in each problem. Okay? Each individual problem might have a different value of x, but once you put x in a problem, it means the same thing every time it occurs. All right, you have therefore 9x squared take 25. No x term. So that's an interesting pattern one. Okay, are we going too fast here? Do you have to go back, practice some examples and come on after? Okay, before we do this little review exercise coming down in a few minutes. Okay, let's go to these now. Example 5. 3x plus 1 squared. 3x plus 1 by 3x plus 1. 3x by 3x, 9x squared. 3x by 1, 3x. Plus 1 by 3x is 3x. 1 by 1 is 1. Oh, something different happening here. We have a repeated middle term. 3x plus 3x is 6x. How did that happen? Hang on, just get rid of that. How did that happen? Well, the two brackets are the same. So we're doubling up the middle term to get 6x. Instead of disappearing, because the brackets are the same, try and understand what's going on here. Because the brackets are the same, you're doubling the middle term. Excuse me. What about this one? 2x take 3 all squared. So write it out. 2x take 3 by 2x take 3. 2x by 2x, 4x squared. 2x by neg 3, neg 6x. Neg 3 by 2x, another neg 6x. Neg 3 by neg 3 plus 9. So with a negative in it, the middle products are still the same, but they're negative. So it's going to come to neg 12x. Okay. Oh, that's interesting. We're going to look at these, and this possibly is where you've left off in Year 8, and this is where we're going to start in the next presentation in Year 9 with these special expansions, if you like. But ideally, you would have seen some of this before, because they only are special cases of your general expansion of two brackets rule there, or FOIL. Okay, let's go. And do you feel confident? So, because I want you to try something now. There you are. Why don't you have a go and see if this has been a bit quick for you and whether we have to go back and revise a bit more slowly. Okay, let's go and have a look. Here are a few review questions. So what I want you to do is to pause the presentation and to have a go and do those three. You can do it in pairs or separately. It's not a test, just to see where you land on your knowledge thus far and where you might start your revision and moving on. Okay, so pause it, and I'm going to do the problems in front of you in a minute. Have a go at those three. All right, come back now. Let's have a look at what this means. This means 3 times x is 3x. 3 times neg 4 is neg 12. Okay, so did you get that one right? Okay, we'll just mark each one as 1. We won't have a mark sim here. Okay. This one, neg 5 by 2x, a negative times a positive is a negative 10x, and neg 5 by neg 3 is positive 15. Watch those signs here. Remember, you've got to bring this with the 5. Any term sign lies to its left. Okay, did you get that one right? What about this one? Let's leave the 7 by itself. 4 by x is 4x. 4 by neg 2 is neg 8. You can see what we've got here. This really, I suppose, is worth 2 marks compared to the other two, but we'll just mark them as right or wrong. So here what we've got two like terms. They're both numbers, just numbers, no letters. 7 take 8. Oh, what's that? Let's go. 7, and then we take 8. We'll be down at neg 1, won't we? Neg 1 plus 4x. And the convention in algebra land is you put the pronumeral term first. 4x, take 1. How did you go? We were able to do those. Otherwise, you have to go back to part A of the textbook and practice from there. Okay, should be able to do this from year 8. All right, let's go down to the next little example. 3 examples here. So pause the presentation. I want you to have a go and then watch me do it. Okay, here we go. This is x by 1 is just x. X by neg x, positive by negative is neg. A number times itself is the square. So that's our answer. Okay, let's look at this one. 3 neg 2 by x is neg 2x. Neg 2 by 4, neg 8. So we've now got, what do you want to do? 3 take 8 is neg 5. Just remember, students forget this. 3 this way, then take 8 will be land you down at neg 5. And then take 2x. So we could put this as neg 2x take 5 with the pronumeral term in the front. Okay, how are you going? And let's have a look at this next one now. Neg 4 by 2x is neg 8x. Neg 4 by neg 3 is plus 12. Neg 1 by x is just neg x. Neg 1 by plus 1, negative times positive is a negative, neg 1. So this is neg 8x, take x. Oh, they're all going negatively, neg 8x. And then you go another one, so this will be down at neg 9x. And 12 take 1. Easy done. Remember, the sign of the 12 is to its left. Sign of the 1 is to its left. 12 take 1 is 11. So that one would be worth more marks, wouldn't it? Because you've got several steps to do there. But we're just going to mark them right or wrong. How are you going with that half a dozen? This is back in the beginning section of the first expansion of bracket stuff. Or if you're not sure, what we've got to do is go back to the textbook and do some more practice examples, because we actually haven't practiced this. We've jumped straight into a review exercise to see what you know. Okay, come down and we're just going to do one more question. I think we've got question 2 and 3, I'm not sure. Okay, expand and simplify. X plus 4 by x plus 7. So we're on to the bigger ones now. So let's have a look. I want you to pause the presentation and have a go. I'm going to do it for you now. Okay, so here we go. X by x is x squared. X by 7, positive 7x. Positive 4 by x is 4x. 4 by 7, 28. Okay, so we've got x squared. These terms are like each other because they've just got a single x in them. 7x plus 4x, you've got 11 of the little creatures. 11x, whatever they are. We don't know what x is. Okay, did you get that one right? Let's have a look at part B. X by x is x squared. X by neg 2 is neg 2x. 8 by x is plus 8x. 8 by neg 2, neg 16. Okay, so we've got x squared, and these two are like each other. 8x take 2x is positive 6x. Take 16. Okay, how did you go? Getting the bigger one here. And I suppose you can just remember the rule. FOIL, first outers, inners last, so you don't leave any multiplications out. You're just multiplying all these together. X by that bundle and 8 by that bundle. Okay, let's go down to this one, and I want you to pause the presentation, have a go. Okay, coming back now, this looks a little bit different. Same system. 1 by 5x is 5x. 1 by 6 is positive 6. Neg x by 5x is neg 5x by x is x squared. And then neg x by 6 is neg 6x. Okay, let's go through. It looks a bit different, this one. Let's start off with the highest powered term first. So let's put neg 5x squared first. And then let's collect up the x's. 5x take 6x is negative x. Right, just remember, we're up here at 5x. We go back, neg 6x will end up neg x on that side, neg 1x. And then we've got left plus 6. So with these, you usually put the highest power of the pronumeral term first, and then downwards from there. Let's have a look at this next one. 2a times a is a by a, so 2a squared. 2a by neg 9, neg 18a, 9 times 2 is 18, and you've got this negative in here. Then we've got 3 by a, neg 3 by a is neg 3a. Don't forget to take the sign with the term, and the term sign is to its left in maths. It's all rules and systems and like another language, isn't it? Neg 3 times neg 9 is positive 27. Negative times a negative is a positive. It's a double sign reversal, if you like, with that negative sign. So we've got the highest power of the unknown there, 2a squared. Let's collect up the terms that are like each other. Neg 18a, take 3a, is neg 21a, plus 27. Okay, very good. How'd you go? Let's have a look at the last little type here. No, almost. There it is. Just come down there. All right. So here's a busy one. There's a couple of things to do in each problem. So I want you to proceed carefully through the expression from left to right using your rules. Have a go and pause it now, and I'll come back and show you. Okay, here we go. It looks big, but let's have a system. X by x is x squared. X by 2 is 2x. 3 by x, 3x. 3 by 2, 6. Then we've got the other term here. 3 by x is 3x. 3 by neg 4 is neg 12. So this is x squared, and then collecting up the like terms. Uh-oh, there's one over here as well. So we've got 5x plus 3x, a total of 8x's there. Can you see that? All of them there are like each other. Then 6 take 12 is neg 6, going the opposite direction along the number line. How'd you go? It looked pretty big, but it's not too bad if you have a system. Let's look at this one. So it's n by n is n squared. N by 5, 5n. Neg 3 by n is neg 3n. And then neg 3 by 5, neg 15. All right, let's go into here now. We've got here negative. Now we better watch the bracket here. So it's going to take away, and we'll do this in a bracket. N by n is n squared. N by 3 is 3n. Neg 2 by n is neg 2n. Neg 2 by 3 is neg 6. Okay. So there's a little trick. I haven't actually been shown that explicitly. You're taking away the whole result of this. So you must do those brackets first. Okay, let's go through now. We've got n squared plus 5n take 3n is 2n. Take 15. Now what are we going to do here? We're taking away all of this. So it's like negative 1 times the bracket. So negative 1 times n squared is neg n squared. Negative 1 times 3n is neg 3n. Negative 1 times neg 2n is plus 2n. You could have collected these up first. And then neg 1 by neg 6 is positive 6. Let's go through and collect terms now. 2n squared, we've got a 2n. And here neg 3n plus 2n. So that's 2n and 2n is 4n. Take 3n is one end, just adding them up, collecting like terms. Could be a bit hard there. Now we've got, oh, I should have collected this up, neg n squared. So that's going to disappear. Neg 15 plus 6 is neg 9. So the answer to this big problem is a simple expression n take 9. You've got to be careful there. Quite a bit of work, and it's really testing whether you're understanding what's going on there. All right, well, how are you going? I think we've pushed our limits here. For the average student coming out of Year 8, that one's a bit hard, and that should be our starting point with practice exercises from the textbook so that we can extend the basics up to there. So I would suggest that that might be good homework for you from that algebra chapter of Hayes and Harris, and this is the, if you like, the end of the B section, I think, there, where we've got bigger expansions there. So have a look in there, and I hope you've enjoyed this first introduction. If you're not sure, you can go back over it, of course, and see how you go. But for now, that's cheers from me. I'll catch you in the next presentation.